Hello and welcome to The People's AI, presented by Gensyn. I'm your host, Jeff Wilser, a longtime journalist for CoinDesk who covers the intersection of AI and Web3. And I'm thrilled to announce a new partnership with Gensyn to bring you the next season of his podcast, The People's AI Season 2. For those new to the scene, Gensyn is a protocol for machine learning computation. Gensyn is building the network for machine intelligence. That includes execution, communication, verification, and coordination software for machine learning operations to be performed pragmatically and permissionlessly on every capable device in the world. So what does that mean and why is that important? We'll be exploring all of that on today's episode. But first, I want to wind back the clock almost 2 years. The summer of 2023, when I was writing a piece for CoinDesk on 10 ways crypto and AI could work together. Now, at the time, this seemed sort of like a fringe concept. There was not nearly the same buzz you see now. I interviewed a ton of experts on the subjects, but one conversation really stood out. I had an in-depth, intense discussion with Harry Grieve and Dr. Ben Fielding, the co-founders of Gensyn. Now, like many folks in the space, they spoke with enthusiasm about the potential for decentralized compute. But what was unique is that unlike many in the space, they spoke with a very sober, clear-eyed perspective on why this is actually really hard. It has tons of potential and they believe in it. It's their North Star. But they acknowledge there's a ton of technical and engineering challenges that need to be overcome, and it takes some time. I love this perspective. I found it so refreshing. And for the last 2 years, they've been some of my favorite folks to speak to in the decentralized AI space. Since then, Gensyn has been quietly building, shipping, evolving, expanding. As you'll hear in this conversation, they started in decentralized compute for very pragmatic reasons. As you'll hear from Harry in this conversation, they explored every avenue of traditional AI research. All of those had limitations, if not deal breakers. There's only one door that made sense, and that was the world of blockchain, crypto, Web3. Now, as you'll hear, they started in decentralized compute. That vision has grown to include a sweeping range of the AI tech stack. We start with their origin story. It's kind of a fun founder meet cute, and then get into the big picture of why this all matters, of how, yes, actual civilization can look different if we get this tech right. Ben articulates a theory of horizontal scaling that's truly revolutionary as compared to the way most people are currently thinking of traditional AI. Along the way, we have some fun nerd out digressions that I think anyone who's deep in AI will appreciate. We ruminate on the actual nature of the models themselves and discuss determinism. Harry, for example, cites the theory of the mind. So the conversation almost tilts philosophical for a bit, and that's one reason I'm so fascinated by this space. So I am thrilled to welcome Gensyn, Ben, and Harry, both as partners for Season 2, and as insightful guests on this very episode. So with that, please enjoy my conversation with Ben Fielding and Harry Grieve, co-founders of Gensyn. Ben, Harry, welcome to The People's AI.
Thank you. Great to be here.
So I don't usually start with origin stories, and I know you've shared your origin stories a bit before, but I got to ask you about how you met, which is Shark Tank meets The Bachelor and how Gensyn was eventually formed. Ben, tell me a bit about what that was like and when you met Harry and how this all came about.
Absolutely, yeah. So as you mentioned, we met on something similar to that, a program called Entrepreneur First, which is an accelerator that is very, very early stage. So instead of taking companies that have an idea and kind of already have a founding team and just need accelerating out into the world, they actually take individuals who meet up in a warehouse in London and form teams together and then build companies in that way. And so Harry and I both joined this accelerator completely as individuals with the backgrounds, like you said, we talked about before, mine particularly in academia, doing my PhD in deep learning and neural architecture research. And Harry's in industry.
Yeah, so my background was in applied machine learning. After my postgrads, where I was mainly focused on econometrics applied to political events, basically, things like riots and hunger, events in society. I joined a risk prediction startup, so they were predicting catastrophe risk, so floods, wildfires, etc. Got very exposed to the compute problem during that period of time. So we were running big models, and they cost us a lot of money as a small startup in London. And it was also clear models were getting bigger. You know, the Transformers paper had come out, GPT-1 and 2 had been released. Everything was kind of, all roads were kind of leading to Rome. I quit my job as a consequence, and I wanted to build a company which solved one or kind of two of the problems around that space. Principally, though, the scaling issue. How do you get this next era of scale? And I met Ben at the accelerator. Basically, they bring a group of people into London from around the UK, and you put you in a warehouse, as Ben mentioned, where you basically network and you form companies. So you come without a team, so it's just you as a person, and basically they match you based on, you know, they kind of, I guess, curate the cohort based on like, you know, the other people there. So it typically, when we did it, had a bit of a deep tech machine learning bend. I think since then it's become more expansive. They've opened up like a San Francisco version of it, you know, it's become a lot bigger. But we met each other on the kickoff weekend, which was the day before it actually started. Love at first sight, and we basically paired up, and that was quite serendipitous because the Monday or Tuesday after that weekend, the global COVID lockdown happened. So the UK shut down. So Ben and I met each other once in person, and then for the next 4 months, we were completely on Zoom. So
the kickoff was particularly interesting because everybody had quit their jobs, they'd quit what they were doing before, they'd moved to London, they'd got flats in London, they were going in person for the very first day. And Matt Clifford, the founder, appeared in front of us, stood in front of us and said, "Welcome to Entrepreneur First, you're all going to build companies, and also this is the last time you're going to be in person because you're all going to go back to your flats in London now and do the rest of this completely remotely," which was a bit of a kind of interesting blow to a lot of people, I think. A lot of people who were in London for the first time and were looking forward to that kind of building in-person vibe. But what it meant for Harry and I was that we spent about 14 hours on Zoom from the small kitchens of our flats in London instead of in the mix in a warehouse where we were expecting to be. But eventually when the lockdown lifted slightly, those 14-hour Zoom calls became very, very long walks along the banks of the Thames instead of remote sessions in kitchens.
When you launched Gensyn, what was the core problem you were trying to solve? And then, as I understand it, this has evolved some over the years. And I'm kind of curious to see how your thoughts have evolved and what kind of area of the tech stack you're looking to play in.
Yeah, I think when we launched, one thing that we both knew was that there was a space of technologies which allowed machine learning to scale across different kind of silos of execution. And so we knew about this technology, federated learning. We'd seen it being applied in these privacy use cases where, for whatever reason, you couldn't move data between different silos. That could be different data centers, or it could be different devices with data on them, but for privacy regulation reasons, you couldn't move that data somewhere else. And so there was a set of techniques which allowed you to split the machine learning models over the data silos. And actually our tagline then became models to the data instead of data to the models. This idea that actually instead of gathering loads of data together and training models on it, you could leave the data split up and train the models at the edge. And so the very first iteration of Gensyn was using that technology directly for the privacy use case. So we looked at financial institutions, tier 1 banks, places that had global footprints of data but couldn't move it around within the organization. And we built solutions for them to use federated learning and various other privacy preserving machine learning techniques to split their models over those data silos and still be able to get insights into the data science and analytics teams. And anti-money laundering, for an example, is a good kind of use case of this, where you have lots of different information about customers, but you can't get all that information into one place. You have to be able to understand it somehow holistically without moving the data around. So that was the first genesis of the technology, but obviously since then we've realized that this is actually valuable in a much larger way if you can build the infrastructure correctly. And so it isn't just data silos that exist in the world, there are other silos of resources. And underneath machine learning, and we selfishly want to unlock all of them, or greedily want to unlock all of them.
Because that was too modest of a goal. Just the original the original problem was, we'll solve that, pretty quickly, and now we have bigger fish to fry.
The core kind of like pivot was to the compute silo. That was the kind of next step, and we realized that we had both had these compute issues, me in industry and Ben during his PhD, where he only had a few GPUs under his desk, and he was competing for likes of DeepMind, who had pods of TPUs in various data centers around the world. It was clear to us, though, that if we wanted to basically bring in this long tail of compute and access that scale, you needed a way to do it such that you could trust the results. Because if you're paying someone to do something and they can either spend hours burning cycles on the GPU to do it, or like pretend they've done it, we all know what the internet's like. People will just pretend, and the outcome's going to be negative. So our focus was, how do you kind of game theoretically move the Nash equilibrium to someone actually doing the work you asked and getting the positive outcome? And that basically put us into research mode. We looked through the literature. We had a long kind of literature walk and review and experiments. And we basically shut every single door in the literature apart from one. And it was probably the one that we were like the least sort of anticipating to be remaining open, and that was crypto. So blockchain, crypto, at the time when we went into it, we thought, it's kind of philosophically interesting, but it has a bad reputation.
You're not crypto bros.
We're not crypto. We didn't come from, maybe we are. I don't know, maybe we are now, but like before something happened. We definitely weren't on the way in. But we had this kind of view that, it's more of a cultural thing than a technological thing.
Before we get into the kind of details of where crypto and blockchain comes in, can you elaborate a little more, Harry, on what that challenge is that you? Because I think the reason I want to underline this is a lot of folks in the crypto world and in like this kind of flourishing world of decentralized AI, they hear this potential and promise of, oh, cool, what if we just kind of cobble together all the computing power around the world, my laptop, your laptop, my smartphone, and together that will unleash compute for all. And it sounds awesome in theory, and I'm not trying to say that can't happen, but when I first interviewed you guys over 2 years ago for CoinDesk, you were really articulate about why, yes, we believe in that, but it's also really challenging, and there's more nuance and more complexities than the average folks realize.
Yeah, so it all starts with the premise of, what are you trying to verify? Like, what is the actual thing here? And there's really two things you can kind of do. You can either be input driven or output driven. So a good example of this is, if all you want is a machine kind of system to give you some output, and you look at the output, and if it's the output that you like, irrespective of whether or not you thought it was the output you were going to get, that's easier to verify because it's verification at the point of receipt. But if you're actually like Ben and I, and you were like practicing machine learning, and you actually want to run experiments, and you want things to actually happen in a certain way, you have opinions about the data and the model that are going to be used, and actually it becomes a lot more complicated because you need to prove that the result you're getting is the output of that function and that input. And that's the kind of initial kind of starting point that we have. From there you think, well, okay, are there certain kind of, I guess, machine learning strategies which are better suited to that setting? And the answer is actually, yeah, there are. So if you're doing kind of embarrassingly parallel tasks, which you can split between lots of different systems. So an example, not a machine learning example, but a good one is SETI at home. Back in the day, in the kind of 90s, people would install this software, would run on their computer. What it did was search for extraterrestrial intelligence. It would look at the night sky. It would get like a little parcel of the night sky. It would run an analysis on your device, and then report back to the central server. Your kind of little patch of the night sky is independent from a state perspective of someone else's, and as a consequence, it's embarrassingly parallel. That isn't the case in machine learning because it's typically state dependent. So, for example, if you're doing generative inference, like something with sort of ChatGPT, when it's working out what it's going to say, it's feeding back the output from the previous token generation event back into the model. So it has this kind of state dependency, and that basically creates two problems. One, it means you can't make it embarrassingly parallel. And two, if you actually want to kind of, I guess, parallelize it in some setting, there's a huge communication overhead. So our problem then became, how do you verify modern machine learning workloads in a way which is simultaneously low communication overhead, plays to the fact that there's state dependency, and thirdly and finally, another complication is deterministic. Because most people don't want this kind of like, maybe it's the right result, maybe it, like type of thing. Usually if you're trying to sell something versus like AWS, where someone like us would have run it previously, you want to know the result's the result. And the issue is a lot of machine learning tasks are deterministic.
As I understand it, Harry, the almost one tricky problem with Gen AI right now is it's all probabilistic, right? And so it's not like math. The cold, hard rules of math don't quite work here. And so because you can't cleanly have this to your input output driven by math, you have this kind of probabilistic universe. Given that it's even within, I'm maybe getting over my skis here, but even if it's on one central computer, it's probabilistic because you don't totally know for sure what the answer will be. So that becomes even more complicated when you go across multiple devices and systems. It gets even harder to verify, is this what it's supposed to be or not? Is it within bounds of probabilistic or is it out of bounds?
I'd say one thing there, which is, it is math, right, that fundamentally, but the difference is that the outcome, the output's just unstable, and it's partially you could run the same thing in the same device and get a different output just by virtue of the way that the operations are being executed versus other operations on the device at the same time. But it gets even harder when you're looking at it between different devices because of the different architectures and like the associativity between operations, etc. Just makes it that even slight kind of differences can actually compound and make wildly different results. And where that matters for us and where it matters in the context of crypto and basically what the big challenge is if you want to kind of have that efficient communication overhead, you want to reduce what you're sending around. And the easiest way to do that in crypto is just to send a hash. So you just send a hash of something. It requires you to do the hashing locally, so you're kind of trading compute for communication. In that setting, the hash is kind of king. You can send it somewhere, you can attest to that thing. However, the hash has to be reproducible. And for it to be reproducible, everything that comes before the hash has to be deterministic. And that's basically the body of work that we've been working on. How do you optimize the determinism and the communication against providing something which works in a kind of state-dependent setting? And we have a solution to that after years of research.
Ben, say a little more about how blockchain, crypto fits into this and the solution you ultimately found after these years of research.
Yeah, I think the easiest way to explain the solution that we initially went for and that we have kind of carried on through the life of Gensyn is probably in the form of three beliefs. And so rather than kind of tackle the problems that Harry described immediately and try and build a full solution that mirrored what the world currently did, we actually kind of pulled back in a sort of systems level way and said, okay, what do we actually believe is persistent through time here? And so underneath machine learning, there are a set of base operations. And we looked at those base operations and we said, these things are very unlikely to change, but the models, the ways they're combined, those really probabilistic combinations that you see in the generative models, for example, those things will change. Harry and I had been in machine learning for long enough to see that every 3 months, 6 months, few years, there would be an entirely new model architecture that would come along in different industries. So I'd seen it in computer vision, Harry had seen it in the risk modeling, we'd both seen it in text generation. We'd seen that these models and these techniques would change, but underneath that, there was this set of base operations, the math that we talked about earlier, the matrix multiplications, etc., the nonlinearities that rarely changed. And so we said, if we're going to build a solution here in this massive kind of gnarly, difficult space, actually we're going to build it from these primitives, and we're going to focus on unlocking the determinism and the verification at those primitives. And then anything you build from that should scale up to the other solutions. And so that was one belief. It was building with the primitives is the most robust approach to take.
Like, here you're right. It's the most foundational level. Everything else is built on top of. Is that a fair way to summarize that? Okay, yeah.
Exactly. And to Harry's point earlier, if you think about verification in that inputs or outputs way, you could do output verification on a transformer by just looking at what it produces and saying, hey, is this right? Can I do some kind of like heuristic machine learning checks on this? But chances are that's only going to work for a transformer. And so if suddenly the space of models changes, you have to rebuild your entire solution. Whereas if you take that input focus and you look at the base primitives, actually, if there's changes in architecture, there's very little for you to change in the infrastructure because you're still just composing blocks which you have made fully deterministic. You have guaranteed that you can verify, you can hash, and you can put them on chain, as Harry mentioned. So that base primitive approach was one of the first kind of beliefs we stuck with. The second big belief was a hard-won one, which was verification ultimately has to have determinism. You can try lots of tricks. You can do distance calculations on outputs. You can try and kind of find them in parameter space or in gradient space, and you can decide if they're within a sphere of each other. But very rapidly, those approaches explode out in complexity, and you can hide anything you want in the kind of exploding space of those distance
Can you give a
calculations.
concrete example of what that looks like?
Sure. I guess one of the simplest examples would be to say when you run inference on any task, the outcome of that inference is a parameter vector of some kind. That parameter vector is a point in space. You could very simply say it's a 2D parameter vector. It's just two values, they're x and y coordinates, and that gives you a point on a graph. And the correct kind of perfect example is another point on that graph. And so if two people run the output, they'll get 2 different points on the graph. That's the probabilistic side of this. You can say, are those 2 points close enough? If I think there's a certain kind of threshold of distance where they're the same, then I'm fine. I can go and assume that. But that distance encapsulates the ability to move things around in the model. And so I could, with a lot of work, minimize that distance in a certain way by changing the updates and changing the parameters of the model to achieve my ends without you realizing, because you're just checking the kind of distance. The pure determinism would give you an identical point on the graph. So it would say, this is exactly in this point. If I run it again, it will be exactly in this point again. And you can't hide anything in the model when you do that, because every single thing has to happen identically. And so our belief, the second belief, was that at some point you need that level of determinism. It doesn't necessarily need to be over the whole model or over the whole training or anything like that. But if you want to have truth at any point, you need to be able to distill down to a full deterministic, if I hash these two things, it's completely identical. And as Harry mentioned earlier, blockchains work on hashes, right? Like there's the data structure that we typically interact with. Hash matches and hash calculations are the kind of technique that underpin those systems. And so if you want to terminate your trust at the consensus of a chain, typically you need determinism and then the ability to hash and have the same outcomes.
On that point, just to give you 2 examples of like what like a bad actor might do. There's kind of 2 genres. One would be they have a kind of laziness attack, which is basically an economic attack in a system. So what they would do is, in that kind of 2-dimensional space, if they can work out, if I do like 15% less work, the output's probably going to be within that threshold around the point. Therefore, I can basically save 15% on my electricity bill, give someone something that gets kind of checked off, and everything's fine. No one's going to kind of view me as a bad actor in the system. I collect my money, and I get to keep it a little bit more by reducing my expenses. That doesn't work because if you were submitting something to AWS or one of the hyperscalers, if you found out that they were actually like under computing what you wanted or something, that would just be a breach of terms. It's a non-starter for most people.
Right.
But that's like the less sinister case. The more sinister case is that inside of that kind of threshold, inside of that kind of distance, someone could inject or poison the model with an attack. And what they could do is they could slip something in which actually completely changes the output of the model in certain settings. So if you're training a model, for example, and you wanted to censor a concept, maybe in the entire kind of parameter space of the Llama 7B model, for example, the actual impact on a generic output for you to censor like Tiananmen Square and the kind of events surrounding it in the 20th century actually doesn't really change the output of the model that much against generic testing, against any of these kind of like parameter comparisons. It looks almost identical. But because it's non-deterministic in the assessment, you wouldn't catch the fact that it's actually been that kind of censorship's been added into the model or that attack's taken place. And then some, days or months or years down the line, someone then uses the model for something and then it gives them an output and they trust it because they've trusted that broken verification system, but it's actually the model is doing something sinister as a consequence. Determinism kills that.
It's almost like, if I hear you right, when it's non-deterministic, there's a squishy margin for error, and that margin for error can be exploited. And so what you're doing is eliminating that squishiness, that margin for error, making it precise, leaving less of a vector for attacks, and also higher quality, higher accuracy output.
Yes.
Is that warm? Okay.
That's correct. I think I would just say that's for not every use case cares necessarily about there being a squishy error. So there's many use cases in the world. Think of a student running a model and seeing what the output is. They don't necessarily want exact bitwise determinism of the full running of that task. But if they want some degree of security, they want some guarantee that it's done correctly, our intuition is that underneath everything, you can still do your distance calculations, you can do probabilistic checks, etc. But at the end of the day, when you want a final kind of check, that final check should be deterministic. So you roll up the distance calculations ultimately to a point of real truth. Otherwise, you're just in this space of distances and probabilities where it's very hard to get any true kind of ground truth, any true sense of in a binary dispute, which one person is correct. And you have to get that at the very end to have any source of trust in the whole system.
I'm trying to square this against my understanding of hallucinations. And my understanding is that many researchers in the traditional AI space have said, hey, like it or not, and I guess no one likes it, hallucinations are necessary for creation for Gen AI, and that if you stamp these out, the outputs won't be as good. And there are teams trying to figure out how to crack that problem. Is the solution you're describing, does that solve the hallucination problem? And where does this kind of sit in the landscape of hallucinations in Gen AI?
I think hallucinations are an interesting, I guess, problem, but also kind of solution in their own right, where it depends what you actually want the output of the model to be. Because if your hallucinations typically come about because you're indexing the model to output something as directed by a user in the format that they want to see, or the kind of thing that they like the model to output. And so a hallucination, for example, if I start asking a model to give me paper citations, the model knows that I really, really want there to be a citation coming next. Right. And so that kind of indexes above the fact that maybe there isn't a correct citation for it to put there that it knows about. So it makes one up because actually that's kind of the best way to get the reward in that situation. So they typically come about from a kind of personalization of models approach. And in reality, as you mentioned, that's kind of what people want. And so we're saying to people, if we take away hallucinations, the models will get worse. It's that they will get worse in their kind of answers to humans. They won't necessarily get worse in their overall correctness. We could make models which are entirely correct, but probably people wouldn't like them very much as chat systems. And so you've got this kind of like this choice you have to make on a sort of spectrum where do you want the model that people sit in front of and they absolutely love but occasionally it lies to them, or do you want the model that is technically correct all of the time but people think this is very dry and not very interesting to interact with? And so from a determinism perspective and from the technology that we do, you probably actually wouldn't really want to solve that problem depending on the use case you're building the model for. But it is solvable if you absolutely want to stamp out hallucinations for a particular use case. You can go down that route and you can not tune the model towards kind of user preferences and things. But typically, we actually want the benefits that come alongside hallucinations.
A model can still hallucinate kind of deterministically though, right? So
Yep.
the actual, I'd say it's a very related category, but it's kind of adjacent to the determinism point. Hallucination's more like if I ask it for, like, as Ben said, like the paper reference or something, and it like makes a paper up, it could deterministically keep making that paper.
They all make it up in the exact same way.
Yeah, exactly, which I guess is fine. The thing that we want to kind of guard against is it to be like exact same prompt, exact same settings, hallucinating like a different paper every time because there's some kind of non-determinism in there. That's like the difference. The actual kind of category of hallucination, as Ben said, is actually quite useful, and frankly, like, depending on your kind of theory of the mind and cognition, like quite, similar to how humans think about things too. So,
it's also possibly unique to, or not unique to, but possibly a result of just next token prediction approaches, which aren't necessarily the best approach to do text generation. You see the diffusion model from Google recently, the Gemini model. We've had state-space models in the past. There's a bunch of different attempts to see actually, is generating text in response to humans best done by probabilistically picking the next token or not? Because when you probabilistically pick the next token and the model knows what the user expects here is a citation and the model doesn't have a citation, it will make one up. Whereas other attempts where it maybe generates the entire answer from scratch and then refines the answer, there may not be a reason to make up a citation in that situation because it's holistically generating the whole thing. It's not dependent on its own previous answer where it's like, well, got to put a citation here. I guess I'll make one up. So it could just be a point in time thing for the current models, and that's one of the reasons, back to the kind of 3 points I was talking about earlier.
Thank you for indulging this rabbit hole, but I think it actually helps kind of illustrate how complex and fascinating all this is. So I took us on a very long tangent, but Ben, back to point number 3 of your 3.
Point number 3 is a deep belief, as the other two were deep beliefs and still are, in scale, essentially. And so we've seen this before in the machine learning space. People invariably believe in scale. OpenAI's big bet was scaling models vertically, throwing hardware and data at them would result in better outcomes. The bitter lesson from Richard Sutton basically says, focus on scaling these things up with compute because that's actually going to be the faster and more effective way of reaching the outcomes that you want. We deeply believe in that continuing. So there's many problems you can look at in the world, which we view as, in some cases, differentiable problems where gradient-based optimization can prove really good outcomes, and in other cases, big search problems where actually there are many possible answers and you're trying to find the kind of best answer in the space of many different things. If you look at the world as one big optimizable thing, our view is if you keep scaling these methods, you keep getting better outcomes. But the kind of final piece, and the bit where maybe it gets slightly heretical, is that we think the era of vertical scaling, i.e. stuffing compute in data centers and just making the model bigger by essentially stacking more GPUs on top of each other to try and scale it up, is actually coming to an end. And the next era is horizontal scaling, where you say, this method worked, but it's become increasingly expensive and there's diminishing returns. Let's actually change the algorithms to allow this to scale horizontally, be more embarrassingly parallel, but take the limits off the scale. And the analogy we could draw back to in distributed systems is the MapReduce moment. Prior to MapReduce, we were scaling these systems in a vertical way. We were throwing more hardware at them to make them more effective. We had supercomputers, we were getting diminishing returns. MapReduce came along and said, basically just change the way you formulate this problem, and suddenly you can horizontally scale it as much as you want. And so instead of doing these 1,000 things linearly in sequence and having the biggest machine ever to do them as fast as possible, just do all 1,000 on different devices, and they do one iteration and the answer comes out. We believe that can happen for machine learning, and so that underpins a lot of the work we do, both on verification, but also on the way we do machine learning ourselves, to demonstrate that actually the moment now is to switch from vertical scaling to horizontal scaling.
That is fascinating. Harry, with those 3 principles in mind, and with this concept of horizontal scaling in mind, talk a bit about kind of where Gensyn is focused on now. You mentioned kind of where the original problem you're trying to crack, and you realize actually it's bigger than that. Our work, our mission is bigger than that. Ben outlined these 3 principles. Kind of where on the tech stack are you focused on, and kind of how you describe the Gensyn mission at this point?
Yeah, so it splits it out 3 ways. There's really kind of 3 levels to what we do. We have the base protocol. That's where a lot of the kind of deepest primitives sit, including the verification. So the verification games we've constructed, for example, our Verdi paper, you can see it at Gensyn.ai/research. It covers the on and off chain kind of interactions required to very efficiently verify machine learning inference and training tasks. We spent probably the largest portion of Gensyn's history in research and focused at that kind of core primitive layer. We've also, in the last kind of year to year and a half, been productionizing the kind of execution side of what we do off chain to get the results bitwise exact between different devices. That includes building our own custom compiler, which as we're kind of commonly told is a company in itself. So having the building a compiler which takes a machine learning graph.
You're the footnotes of some of your problems are entire macro industries. So they're not small chips, not small problems you guys are focused on.
They definitely are. And as a side point, I think it makes the engineering challenges we have here particularly interesting, because it's the kind of some people, particularly in things like compiler and reproducibility, making things reproducible actually, the vast majority of machine learning isn't reproducible because the speed up increase which you get from non-determinism is kind of one of the big unlocks, which is fueled the most recent kind of advances in scale. But there's actually a pretty significant minority of people who are really interested in it conceptually, but they don't actually have a place to deploy it in real life. And this is actually a very nice example of where they can deploy it. So we actually find people of all different kind of stripes and colors joining the team, because they come from these backgrounds which are actually well suited in this very interesting case. But that's the kind of core level. We then have a kind of abstraction level which abstracts a lot of this and makes it kind of more consumable, kind of more like a kind of platform layer, and we're currently building that just now. And then at the highest level, we have the kind of communication frameworks and the use cases which are used to fully leverage all that lower level technology. As a company, we're increasingly focused at that kind of second and third level. So we have a test net up and running just now. We internally have kind of smart contracts deployed which are able to do the verification game.
Is this where RL Swarm sits? Is that how this fits into this?
Yeah, so RL Swarm's at the highest level. That's the kind of communication paradigm that we use. It's peer-to-peer reinforcement learning. We're about to do a large release which generalizes that even more to other use cases. And on top of that, we have a variety of additional training strategies. So for example, just today, literally an hour before this call, we released No Local, which is our optimization strategy that doesn't use an all reduce, it just uses gossiping, which is important because it significantly lowers the kind of overhead required in order to, and then the kind of synchronicity required in order to train models. So there's a lot of kind of research work happening there. In the next kind of epoch of Gensyn, we're basically taking all of that engineering and research work that we've done and we're pushing it into mainnet, and then with essentially kind of first-class products that people can use to leverage it. The kind of core reasons you'd use our protocol are basically threefold. One, scale. You get enormous scale when you kind of step outside of the sort of existing, paradigms that Ben mentioned for training large models, like the kind of OpenAI kind of vertical scaling data center approach. The second piece, which is interesting, is there are use cases which require verification, just kind of like a standalone thing. There are use cases where you want to know a model has executed something in a way which is faithful, and you don't trust another party to execute it.
I'm guessing financial transactions.
Any kind of crypto-economic transaction which is determined by a machine, or needs to be determined by a machine, or if you need a trusted third party to execute a model to kind of settle a transaction or settle some kind of output of a model which would have otherwise happened in real life, or if you're building kind of games or anything which has this kind of programmatic but sort of generative component to it, where you need the result to kind of be I guess, arbitrated by something. You need to know, like, if you're playing against an AI player, is it actually
right? Or I'm guessing agents, right? The new blossoming agentic economy. This is central to that.
This dovetails with the third category, which is basically, we think that in the next 5 years, the human kind of economy will be eclipsed by this kind of machine economy, which is growing alongside it. It's increasingly sort of non-contrarian opinion that in the next 5 years, things are going to look extremely different, and we're going to have machine systems which are not just kind of making human transactions with humans, but also just making transactions with each other and doing things in a completely kind of autonomous way. That needs a kind of substrate that it can sit on, which is obviously permissionless, completely programmatic, and untrusted. That's what we're building.
One final point, when we think about verification, we talk a lot about arbitration and kind of being a trusted third party, but you can kind of very easily see that in the human world with any decision that has a judge, for example, any legal situation where you need a final person to make a decision. We talk a lot about making machines able to do that, and so we can arbitrate the decisions between machines, but actually there's also huge benefits in the human world. If you just say, replace a judge with a deterministic machine, which can now understand human language, you actually have a potentially much better judge. And so there's many different parts of the world, both human and machine, where having fully deterministic execution, where you and I could opt in and say, this machine learning model that we've both seen trained deterministically will be the judge if we ever dispute this contract we've just signed. And in the future, we know we both trust that judge. It's not going to be manipulated by either of us. There's not going to be strange biases behind that judge. Maybe, I don't know, something happens in that judge's life and they suddenly start to like you more than me. None of that is going to happen because we've both opted into something which is a machine and is fully deterministic. And so that's essential for machines. They can't exist and kind of arbitrate disputes without it between themselves. But it's actually a huge efficiency unlock for the human world and makes us much more effective at arbitrating disputes between ourselves. And so essentially being able to arbitrate with a trustable, not non-biased, but known bias machine is a very effective tool in many different areas of society.
I'm glad you went there, because I was going to ask, as we wind down, say a little more about how this concept of horizontal scaling, how that could impact the world in an everyday fashion. Or put differently, if we get this right, if this all breaks the way you want, if you guys crack all the problems you're trying to solve, what are some of the benefits to the world? And kind of get into what's the North Star of Gensyn, of why you're doing this, of how you think this will really change the world?
Yeah, so ultimately, humans just get much more effective, which is generally the kind of improvement of every technological advancement, is whatever we're doing as humans is now being done faster, more effectively, more efficiently, etc. And so this technology is no different. It does exactly the same thing. In our view, it does it through essentially two different angles. There's autonomy, like Harry said, which is taking things that a human was doing right now and just saying, hey, actually, a machine can do that thing. And so the human doesn't need to do it at all anymore. Maybe the human just asks for it, like you would ask another human for it now, but instead, without you noticing or even caring, the other party, when you've asked for something to be done, is just a machine now. And instead of them scaling through biology, i.e., if you wanted more people to do that, you'd need to make more people, they scale through electricity. If we need more machines to do the tasks, we just need more electricity, we need more chips, etc. We manufacture more and we can do more. So that's the autonomy piece. The second piece is augmentation. The things that we don't necessarily want to farm out to a machine, but we do ourselves as humans. If you think now, when I'm kind of searching the web and I'm looking for information, I could say, oh, I would like a machine to do that and write me a research report, but that's not always the case. Sometimes you yourself just want to be more efficient at that individual task because you as a human are bringing some unique aspect. And I think a lot of people in the machine learning space right now are trying to decide what they think those unique aspects are and then design around them. Our view, as many of our views you've seen so far, is much more principle-based, which says we don't necessarily know which bits humanity is going to want to carve out and automate and which bits we're going to want to keep for ourselves and augment. So let's build technology to do both of those things and let the market determine where to do it. And so we will see agents come about and take away tasks from humans, but we'll also see machine learning models just improve human effectiveness at tasks, where for whatever reason, the market decides that a human should sit at the center of this task and should be the person kind of driving the task forward. You can also view this in a machine learning focused way, where you look at current systems focusing on verifiable rewards. So the reinforcement learning reasoning systems like DeepSeek R1, etc., they moved us away from supervised learning, where a human had to label many images or many kind of tasks and then train a model to replicate. It moved to creating an environment with rewards and allowing a model to explore around that environment. That's still creating autonomy. The next stage could be, don't create verifiable rewards, just passively assist a human. And in doing that, your reward scenario is just, does the human get better at whatever they're doing? The model doesn't need to know what the human is doing. And in building something like that, you actually zero shot any task a human does in the future. Whereas in the current kind of autonomous approach, you would have to have somebody sit down and say, right, I need the model to do this exact task. I need it to have a reward signal. I need it to have data. I need to train it up to do that task. And so it doesn't ever generalize as far as you possibly could. To tie all that together, augmentation and autonomy, realistically, the way that will present itself to us as humans is just a change in every technical interaction we have to have models behind it. So now when we use applications, there's code running in that app, there's kind of paths that a human sat down and coded up and said, when they click this button, they need to then click this button and then this button, and every user gets exactly the same experience. That starts to fade away and it becomes more probabilistic, because behind the scenes, every app is either trying to take tasks away from you or augment you in some way, and it's inferring what it is that you need to do. And so your interaction with Riverside, for example, may be completely different to mine, because the app itself, through its machine learning model, knows that you're coming in to host and Harry and I are coming in to join. And so we get a completely different interface, but a developer didn't have to sit somewhere behind the scenes and code up 2 interfaces. Actually, there could be thousands and everybody gets a completely different one. And so put that premise behind every single technical interaction we have, and you get a completely different system of technology that just makes us more effective and scales the parameter space of models across the entire world.
Ben, that is a wild, exciting view of the future. Thank you both again so much for taking time to break this down. These are not simple problems you are solving, and I think the implications and upside is more sprawling I'd even imagine before this conversation. Can't wait to dive into more in detail in future episodes. Thanks again, and I'll talk to you guys soon.
Likewise. Thanks so much. Cheers.
Well, there you have it. Thanks again to Dr. Ben Fielding and Harry Grieve, the co-founders of Gensyn. And as you've probably gleaned from this conversation, Gensyn is a protocol for machine learning computation. It's building the network for machine intelligence. That includes execution, communication, verification, and coordination software for machine learning operations to be performed programmatically and permissionlessly on every capable device in the world. And thank you to you, dear listener of the People's AI. If this is your first time here, please subscribe. We're on all the usual platforms, Apple, Spotify, YouTube. And this podcast itself, we're in growth mode. We're scaling. So if you enjoyed it, it'd be great if you could share it on social, rate it 5 stars, send to a friend. Thanks again, and see you next time.